So very good day to everybody. This is machine learning, okay, and in this class we discuss about transparent neural networks. Actually we are discussing about neural network, artificial neural network, convolutional neural network. So in this class we'll discuss about transparent neural network. So this is especially for you, my dear students and young researchers, and you can reach me at dr.christoananth@gmail.com. So before beginning the session, once again, let me thank God for giving me this opportunity to deliver this useful session to share my knowledge among my fellow national, international participants, students, and young researchers. Right. So in this class, we discuss about superhuman artificial intelligence systems. Then we discuss about black box technology, whether you can actually trust the black box technology, okay, and why you should actually interpret something you are picturizing as a object, that how the human brain can be able to understand. So that we'll discuss. Then we discuss about layer wise relevance propagation, how you try to open the black box, what is the decomposition procedure, how you can explain it, okay, and finally you are going to measure the quality of the explanations. So at regular intervals I'll be giving you some short videos to discuss the knowledge in our topics, right? So this is superhuman systems. As you can see, like we have several things like game go, that's a game. Texas Hold'em poker game, cards, okay. Image classification based on different images, traffic sign recognition like stop or maybe bridge, okay, right turn, left turn, IQ test, okay, computer games, uh, share market, okay, trading, drone control, cancer detection, or maybe skin cancer detection. Everything we have systems, artificial intelligence based systems, that is going to categorize it, okay. So you can call it as the superhuman artificial intelligence systems. Last class we actually discussed about Bayesian classification, whether a person has cancer or not. What is the percentage that a person has cancer? What is the less chance that the person will not have cancer? So that we can classify with the help of systems. So no need of human beings, we can use the systems to categorize, okay. So these are the different ways where the systems can propagate, okay. And then we have like black box technology, okay. We have a car, we have some devices for performing equipments, I mean the operations. Then we have from the chimneys smoke is actually coming, okay. So our concern, okay, whether to trust these black boxes or not, okay. So why interpretability? So we will have to verify that the systems works as expected, so which means that whatever we are giving the input, it should produce the output, okay. So wrong decisions can be very much harmful, especially medical domain, okay. If you are saying uh, cancer bore, which means that immediately sometimes the people will have high blood pressure and maybe they will try to suicide also. So you have to be very careful about what you are trying to do, okay. And then you are trying to understand the weakness of the system also. Here we are going to detect the biases, okay, bring in human intuition, and of course you are going to improve and then enhance the system, okay. So this is what you are going to learn from the AI system, okay. So I've never seen a human play this move, which means that the human, whatever the human is doing, similarly the system is also doing, okay. So what you are going to learn from the AI system, okay, and apply the artificial intelligence to the sciences also. So why you are going for prediction, so that you should be having an answer to it, okay. And then we have the legal aspects, the right to explanation. For example, something you are explaining, what is, why you should do that, or what is the justification that you will do. For example, if you are saying x is equal to 5, why x is equal to 5, you have to give the explanation. So you are actually responsible for whatever you say, okay. So that is retaining the human decision. So here we will have different dimensions of interpretability, like we will have the prediction, we have the model, and we have data event. So in the prediction, we will explain why a certain pattern of X, okay, has been classified in one particular way. Then you have data, what are the dimensions that is actually relevant for that particular task. And then we have model, okay, what would be the pattern that would be belonging to that particular category, right? And then we will have model. So what would be a pattern belonging to a particular category, okay? So that looks like according to the, or maybe aligned to that particular model, okay? So we will have train interpretable model, okay? So it's suboptimal or maybe biased even based on linearity, sparsity even, that you are going to compare with the training the best model, and you have to interpret it. Interpreting means you are going to understand it, okay? So here you are going to go with the black box idea, okay? So summation RP, okay? So that is the measure of how much like each pixel is going to contribute to the overall prediction, okay? So that is equal to f of x, okay, right? So this is the layer wise relevance propagation, okay? So this is an image, okay? So this one you can go it into the black box, okay? So this you are going to categorize it as a image, okay? So here it will be identifying the most significant parts. For example, here the red thing is there, okay? So that is categorized as yellow here, okay? And the remaining parts are actually eliminated or maybe discarded. So which means that everything it's a green screen for which the higher intensity pixels are maybe illuminated, okay? So this is the classification. For example, in the image you have chicken, okay? You have chicken, okay? Backdrop, if you can see, there are flowers, there is some cat, there is some dog, that and all we are eliminating, okay? So everything we are getting, but we are taking only the chicken or maybe the rooster, okay? So what makes this image a rooster image, which means that here you are going for initialization rj l plus 1 is equal to f of x. So that actually comes from this equation, okay, which is equal to f of x, okay? So from this one, okay, so you are going to redistribute this evidence for the class rooster back to the image space that you are going to convert, okay? So this is the explanation. So what is the significant measure, okay? So we go for deep layer decomposition, okay? We'll take rooster, okay? So rg power l plus 1, so that we will be categorizing. So ri power l is equal to summation over j, okay? So here we'll go with the alpha beta rule, okay? So alpha xi, the weight factor wij, okay, divided by summation over I xi plus wij, okay, plus beta xi wij divided by xi, you have xir multiply by wij, okay? So that is what you are going to go for, and then you multiply by rj power l plus 1, okay? So here if you can take the total factor should be equal to unity, okay? Like alpha plus beta should be equal to 1, okay? So this is the thing, okay? From this one, finally what you are going to get that image, you are going to identify the most significant pixels that are corresponding to this one, okay? So here if you are taking, this is actually encryption part. From that, see, from here I am talking, from here I am talking, from this one, okay, you are actually going to get, okay, the cat, rooster and then dog, okay, out of which you are going to highlight the most significant pixels, okay? So this is the layer wise relevance conservation. So summation over ri is equal to summation ri power l, which is equal to summation rj power l plus 1, okay? We have the function to be equal to f of x, okay? So summation Ri is equal to f of x, that is actually the Taylor decomposition. So f of x is equal to the initial condition f of x naught, okay, plus summation dou f by dou xi, okay? So that is nothing but xi minus xi bar, okay, plus order factor, okay, xx transpose, okay? So here we are going to achieve for the linear models, and here you are going to go with the deep ReLU networks without biases even. So x is equal to limit epsilon tends to 0, okay, epsilon x, which is equal to 0, okay? So there are two reasons why we are actually going for Taylor decomposition and why it is not actually giving the results, okay? So here, in order to find the root locus point, it's very hard, okay, which means that too much of information is actually needed, and which means that it will have a negative evidence, okay? So this is the root locus point. And second one, we'll have the gradient shattering problem, okay, which means that the gradient of the deep nets would be having a very low information value. So that is the reason we are not going for the Taylor decomposition method, okay? So here if you can see, like neural networks, if you can see, it will be composed of small functions, and we actually propose a deep Taylor decomposition. Okay, so first of all, the major function f of x we are going to decompose into sub parts of the decision function. And what you have to do, you have to explain each of the sub functions, and finally you are going to accumulate or maybe aggregate the explanations, and you have to find out with respect to x1 and with respect to x2, you are going to find the relevance. Okay, so here we will go with the Taylor decomposition. Okay, so del f. Okay, so f of x, so here del f, okay, the transpose x is equal to x bar, okay, for x minus x bar plus epsilon. Okay, so this one you are going to take it as r1, and this one you are going to take it as r2 plus the factor epsilon, we are going to add them. Okay, so here we will be having a modification of the Taylor decomposition algorithm. So Taylor decomposition in the present form, it cannot be applied, but if you go for deep network or maybe deep Taylor decomposition, then you will go for h1 plus h2 plus h3. So here we will be categorizing as individual Taylor decomposition, h1, h2, h3. So everything has been interlinked. Okay, so here so from h1, here you will go r2, and this one r1 and r2, and this one r1 and r2. So from this you are going to establish a linear relationship between r1 and r2. So f of x is equal to r1 plus r2. Okay, so this is actually the relevance propagation. From the input we are propagating, okay, through the feed forward network. Okay, and back from the output we are actually traversing the path event. Okay, so which means that that's another one question, like rk, whether it can be explained as a function of aj. Okay, so that is nothing but the similarity factors, whether it can be explained. Okay, also whether you can perform a measure like rk of aj, whether you can actually go for computation of r1 and then r2. Okay, right. So what you are going to do, this rj, okay, alpha aj, okay, wjk divided by summation aj wjk minus beta aj wjk divided by summation aj wjk. So this one you will differentiate, okay, into two. One is intuition and another one is analysis. For example, if you take in the case of the image, okay, this is the image, and for this one you are going to highlight only the most important parts, that is the sensitivity analysis, and from this one, okay, so most significant parts, that you will go with the decomposition process. Okay, deep Taylor decomposition process. Okay, so with the sensitivity analysis you are going to explain what influences the prediction cars. And deep Taylor decomposition, it is going to explain the prediction cars as it is. Okay, so here if you can see car, everything has been explained. Okay, so the slope decomposition associated with the sensitivity analysis, you will go with ri equal to del xf. Okay, so that is the modulus the whole square. And similarly deep Taylor decomposition, it is summation over ri equal to f of x. So normally deep Taylor decomposition is the best method in comparison with the old Taylor decomposition method. So this is how you are going to distinguish between positive relevance as well as negative relevance. Okay, so that is the your image you will be having. So class 3, okay, you will be having some pixels that are associated, and similarly class 9, okay, it will be removing all those blur one, and it will be very finely drawing the tree. So this is how you try to measure the quality of explanations. From the image we will go for sensitivity, then you go with the deconvolution. See, in the deconvolution we saw the exact picture of a crow or maybe the bird. Okay, and from that you are going for LRP. Okay, so that is how you will go with the linear technique. Okay, and you are going to measure the heat map also. For this one you are going to sort the pixel scores. Okay, and here you are going to iterate the flip pixels, evaluate the f of x, okay, and measure the decrease of x. So from this image you are going with the method, okay, to actually get this one. Okay, and we will have modified National Institute of Standards and Technology data set. Okay, so that in terms of LRB, sensitivity and random, we will be finding, okay, the factors, the sensitivity factor. Okay, so that you will compare with the pixel flips, okay, versus the score of the correct class. So here it will be 0.722, here 0.691, and random method is 0.523. Okay, so normally LRP method, okay, so that is most suitable method in comparison with the MNIST dataset. And we'll have complex data sets also, like images, complex images also, our LRB profile is going to perform better. Okay, so these are the different image sets. For example, Sun 397 has 397 scene categories, and we have 108,754 images. That much image we have. Okay, also we have ILSVRC, MIT places, we have several image sets, and in comparison with this one, with regards to steps, okay, and with regards to relative to random, we will be experiencing, the graphs that are associated, and we have concluded that LRP method was the best in comparison with the all other methods.